Black holes existed on paper long before they existed in telescopes. In 1783, John Michell used Newton's gravity to imagine dark stars, so compact that light itself couldn't escape. In 1916, Carl Schwarzschild found an exact solution to Einstein's new theory of gravity that described the same idea. For decades, they were nothing more than mathematical curiosities. There was no way to know the universe actually built such monsters. Cygnus X1, the first strong black hole candidate, wasn't identified until the early 1970s. The first direct image of a black hole silhouette arrived in 2019. If something as extreme as a black hole could hide in the equations for generations before we confirmed it, what else is still hiding there? In this video, I want to explore a set of ideas that sit right on the boundary between serious physics and the unknown. Stars made largely of vacuum, called Gravastars. The time-reversed twins of black holes, white holes and wormholes to other universes. And the possibility that our cosmos is just one universe in a vast multiverse, invoked to explain one of the biggest numerical mistakes in physics. None of these have been observed. Some may turn out to be impossible, but all of them are rooted in real equations, not just science fiction. To understand how far we can push those equations, we first need to understand how ordinary stars defy gravity in the first place. A star is a never-ending contest between gravity and pressure. Gravity always pulls the star's material inward. Left alone, a cloud of gas will keep collapsing. What stops that collapse, at least for a while, is pressure pushing outward. In the sun, that pressure is generated deep in the core. Protons collide and fuse into helium in nuclear reactions that release energy. That energy escapes, not in a single flash, but through a chaotic, random walk of photons and hot plasma, pushing outward on every layer of gas above it. This delicate balance, hydrostatic equilibrium, is what defines a star. Inward gravity, outward pressure, everywhere inside almost exactly cancel. Change either side too much and the star adjusts or dies. But fusion doesn't last forever. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core. Fusion will briefly move into a shell around the core. The outer layers will puff up and the sun will become a red giant. Eventually, even helium will be spent. The core will collapse, not because gravity got stronger, but because nothing is left to generate thermal pressure. As the core is squeezed to tiny volumes, quantum mechanics steps in. Electrons cannot all occupy the same quantum states. They resist being packed too tightly. That resistance is called electron degeneracy pressure. The collapse stops. What remains is a white dwarf, a star's core shrunk to roughly Earth size, supported entirely by electron degeneracy. No fusion, but still a stable object for a while. There is a price for relying on electron degeneracy. It has a hard upper limit. Subrahmanyan Chandrasekhar showed in the 1930s that a white dwarf can't be more massive than about 1.4 times the sun's mass. Beyond that, electron degeneracy pressure must give way to gravity. That value is now called the Chandrasekhar limit. If a collapsing core ends up heavier than that, gravity forces electrons and protons to merge into neutrons. The matter becomes so dense that a teaspoon would weigh billions of tons. Again, quantum rules intervene. Neutrons also obey a Pauli-style exclusion principle. They generate neutron degeneracy pressure, which can support a star of up to roughly 2 to 2.3 solar masses, depending on the exact physics of super-dense nuclear matter. Those objects are neutron stars, tiny, city-sized, and the densest clearly observed stellar remnants we know. What if even neutron degeneracy pressure isn't enough? If the collapsing core is too massive, above about 2 solar masses, maybe a bit more depending on the equation of state, no known kind of ordinary pressure can stop gravity. The object's radius shrinks toward its Schwarzschild radius. the size where the escape speed reaches the speed of light. Once the surface falls inside that radius, an event horizon forms. From then on, even light emitted outward can never make it back. For the outside universe, the collapse effectively freezes at the horizon. Inside, the matter keeps crunching down toward a singularity, at least in classical general relativity. At that point, we stop talking about a star and start calling it a black hole. But general relativity and quantum theory leave us with a nagging question. Is this really the end of the story, or just the end of the story for ordinary matter? To go beyond neutron stars, we need to push on the limits of Einstein's equations themselves. In 1959, Hans Buchdahl proved a powerful result. For any static spherical star made from a normal fluid, meaning it has positive energy density, positive pressure, and behaves reasonably, the radius of the star must be larger than 9/8 of its Schwarzschild radius. That's only 12.5% larger than a black hole of the same mass. But it's a hard limit for matter that satisfies those assumptions. It tells us two things. One, you can't compress realistic matter arbitrarily close to a black hole without actually forming a black hole. Two, if you ever see an object that's even more compact than Buchdahl allows, you've discovered matter that breaks at least one normal rule. And that's where exotic possibilities like Gravastars enter. Physicists have proposed several kinds of exotic compact objects, or ECOs, that might sit between neutron stars and black holes, or even impersonate black holes entirely. Some examples: quark stars, where neutrons dissolve into a fluid of quarks; boson stars, made from scalar fields instead of particles like protons and neutrons; dark matter stars, held up by interactions of unknown particles. But one of the strangest ideas is the Gravastar, short for gravitational vacuum star. In 2001, Pavel Mazur and Emil Matola suggested a very different interior structure. The outside looks just like a Schwarzschild black hole, but inside, instead of normal matter, you have a region filled with something like pure vacuum energy, constant positive energy density, and negative pressure with P equals minus rho in natural units. Separating this interior from the exterior is an ultra-thin, ultra-dense shell of exotic matter. In such a configuration, the space-time inside is effectively de Sitter space, the same sort of geometry we use to describe cosmic acceleration from dark energy. Gravity inside cancels out. No net pull in or out. Objects would float freely, as if in a perfect weightless lab. Why does this vacuum like interior matter? Because in general relativity, pressure gravitates too. For a fluid with energy density ρ and pressure P, the combination ρ plus 3p over c squared controls whether it tends to slow or accelerate the expansion of space. Ordinary matter and radiation have positive ρ and non-negative p. They attract and decelerate expansion. Vacuum energy is different. It has positive ρ but negative pressure, with P equals minus rho c squared. That combination flips sign and acts repulsively on large scales, driving accelerated expansion. In cosmology, we call this dark energy. In a Gravastar, the same kind of equation of state is confined to a spherical region. Inside, the repulsive effect of the negative pressure exactly balances the attractive effect of the energy density, leading to no net gravitational acceleration. So in a sense, a Gravastar is a star whose stuff is more like the vacuum of space than like atoms, and its very existence would tie together stellar astrophysics and the cosmic acceleration of the universe. Mathematically, you can tune a Gravastar so that its radius sits arbitrarily close to the Schwarzschild radius, but never quite crosses it. That would make its external gravity field almost indistinguishable from a black hole's. So how would we know the difference? Two main ideas are being explored. One, electromagnetic signatures. In a true black hole, Any light emitted inside the event horizon never escapes. In a Gravastar, there is no horizon. In principle, radiation could reflect from the ultra-dense shell or leak out slowly, creating subtle differences in the radiation from matter orbiting near the object. 2. Gravitational wave echoes. When two compact objects merge, LIGO and Virgo record a characteristic ringdown as the remnant settles. A black hole's ringdown should decay smoothly. Some Gravastar models predict additional weak echoes of gravitational waves as disturbances bounce off the inner surface and leak back out. Searches for such echoes in existing gravitational wave data have produced tentative claims, but nothing widely accepted. Many analyses find no statistically convincing evidence. At present, every observed candidate is consistent with the simplest black hole models. That doesn't completely rule out Gravastars, but it does constrain how they could behave if they exist at all. In early 2023, a research group led by Chris Pearson and colleagues reported something provocative. An analysis of massive black holes at the centers of galaxies seemed to show that their masses had grown over billions of years in a way that mirrored the growth of dark energy. They proposed a bold idea that black holes might themselves be made of vacuum energy, more like Gravastars than like classical singularities. In that case, black holes could be both the seeds of galaxies and the source of cosmic acceleration. The response from the community was swift and skeptical. Other astronomers argued that the data were compatible with more conventional growth from accretion in mergers. Theorists pointed out tensions with how we understand energy conservation and cosmic expansion in general relativity. As of now, the black holes or dark energy idea is an intriguing speculative model, not a consensus view. But the fact that such a proposal can even be formulated shows how close the mathematics of Gravastars, dark energy, and black holes really are. Black holes are not the only exotic object hidden in Einstein's equations. If you take the mathematics seriously and ask for the most complete, maximally extended solution describing a non-spinning black hole, something surprising appears. A mirror image object that can't be entered, only exited. To build some intuition, think of a mathematical cone. The simplest equation for a cone in three-dimensional space doesn't give you a traffic cone. It gives you two cones joined at the tip, one pointing up, one pointing down. Real physical cones are just halves of this idealized object. The Schwarzschild solution has a similar double structure in time. The part we usually call the black hole describes a region from which nothing can escape. But the fully extended solution also contains a region you can't enter, only exit. That's the time reverse of a black hole, and we call it a white hole. Penrose diagrams are a way to compress an infinite spacetime into a finite, causal map. Light always travels along 45-degree lines. In the maximally extended Schwarzschild diagram, there are four key regions. Region 1, an exterior universe like ours. Region 2, the black hole interior, where everything that crosses the event horizon ends at a singularity in its future. Region 3, the white hole interior, where there is a singularity in the past. Light and matter can emerge from it, but nothing can fall in. Region 4, another exterior universe, causally disconnected from Region 1, except via the /white hole structure. Mathematically, the same metric that describes a black hole also describes this white hole in a second asymptotically flat universe. Does this mean white holes actually exist in our cosmos? Not necessarily. The Schwarzschild solution we just drew assumes the black hole was there forever, with perfect symmetry and no collapsing star. When you model a real stellar collapse, you get a black hole region, but no white hole region in the past. So white holes are absolutely allowed by general relativity, but whether nature ever chooses to make them is a separate question. Things get even more exotic when black holes spin. Real astrophysical black holes almost certainly rotate, and their geometry is described by the Kerr solution. Kerr black holes have two horizons, an outer event horizon, like the Schwarzschild case, and an inner horizon, a surface beyond which the gravitational pull toward the singularity weakens again. In the idealized Kerr spacetime, you can, in principle, fall through the outer horizon, thread your way around a ring-shaped singularity, cross the inner horizon, and emerge into a different region of spacetime. The full Penrose diagram repeats an infinite tower of universes connected by black hole and white hole regions, a kind of mathematical wormhole network. This is the origin of the idea that a spinning black hole could be a portal to another universe. But most relativists think this picture breaks down in reality. The inner horizon of a Kerr black hole is believed to be violently unstable. Any small perturbation or infalling matter triggers mass inflation that likely destroys the nice wormhole structure. And quantum gravity almost certainly modifies the core. So while the Kerr diagram is a fascinating mathematical playground, it's probably not an accurate roadmap for inter-universe travel. We know classical general relativity breaks down at very high curvature, near singularities. Quantum gravity should take over, but we don't yet have a complete theory. One contender, loop quantum gravity, treats space-time itself as built from discrete loops. In some loop-based models, the collapse that would classically form a singularity instead undergoes a bounce. Applied to black holes, this leads to a provocative picture. As a black hole evaporates via Hawking radiation, it shrinks. When it becomes extremely small, around the Planck mass, quantum effects make it more likely to tunnel into a new phase. That new phase behaves like a white hole, slowly disgorging the information that fell in long ago. The interior volume of such an object can be enormous, even if its external size is microscopic. Carlo Rovelli and collaborators have argued that these Planck stars, or white hole remnants, might solve the black hole information paradox by delaying the release of information to far future times. Some have even speculated that explosive final stages of primordial black holes could show up as mysterious bursts of high-energy radiation today. As of now, no such signals have been convincingly tied to this scenario, but it remains an area of active theoretical work. General relativity predicts another singularity besides those in black holes, the one at the very beginning of our universe, the Big Bang. In a purely classical description, the universe seems to have started from infinite density and curvature. That's suspiciously similar to the past singularity of a white hole. Loop quantum cosmology, a simplified application of loop quantum gravity to the universe as a whole, suggests that instead of a true beginning, our Big Bang may have been a big bounce, a transition from a previous contracting phase into the expanding universe we inhabit. In that sense, you can think of our cosmos as emerging from something white hole like an apparent space-time. We may never be able to see beyond our own cosmic horizon to test this, but it's a striking example of how white holes fit naturally into attempts to marry quantum mechanics and gravity. So white holes are not just science fiction opposites of black holes. They may be part of the deeper story of where our universe itself came from. Let's step back from compact objects and look at the universe as a whole. Observations of distant supernovae in the late 1990s, along with measurements of the cosmic microwave background and large-scale structure, showed that the expansion of the universe is accelerating. Distant galaxy clusters are not just receding, they're receding faster and faster. In Einstein's framework, this means that on the largest scales, there is some form of energy with negative effective pressure dominating the universe, something that acts a bit like the Gravastar interior, but spread throughout space. We call this dark energy. Today, dark energy appears to make up about 70% of the total energy density of the universe, with an equation of state parameter W very close to -1, consistent with a cosmological constant or vacuum energy. If dark energy is just vacuum energy, the energy of empty space predicted by quantum field theory, then in principle we can try to calculate its density. Here's the problem. Those calculations blow up. Every quantum field has so-called zero-point fluctuations, and if you sum their contributions up to some high-energy cutoff, you get an enormous energy density. Depending on the assumptions, the naive theoretical value can be between about 10 to the power of 68 and 10 to the power of 113 joules per cubic meter. The actual measured dark energy density is around 10 to the power of -9 joules per cubic meter. That's smaller by somewhere between 60 and 120 orders of magnitude. This mismatch is sometimes called the worst theoretical prediction in the history of physics. It's the cosmological constant problem. Why is the vacuum energy so astonishingly small and yet non-zero? If the vacuum energy were much larger and positive, the universe's expansion would have accelerated so quickly that matter would never have clumped into galaxies and stars. If it were large and negative, gravity would have quickly reversed the expansion, leading to a catastrophic big crunch. So the value we observe, tiny but not zero, seems to sit in a narrow habitable window, high enough that the universe eventually accelerates, low enough that billions of years of structure formation could unfold first. In 1987, Steven Weinberg used this idea to make an anthropic argument. He reasoned that if there is a range of possible cosmological constants, then the only universes in which observers can exist are those where the constant is low enough to allow galaxy formation. From data on early quasars, he estimated an upper bound for this life-friendly value. Remarkably, when dark energy was later measured, the real value turned out to be only 1 or 2 orders of magnitude below Weinberg's anthropically motivated upper limit. That's not a precise prediction, but it is suggestive. It tells us that the vacuum energy we see is just small enough for galaxies, and by extension, for life. But there's a remaining discomfort. Why should we live in a universe whose vacuum energy just happens to fall in the extremely narrow range compatible with life? One radical answer is because there are many universes and we can only exist in one of the rare life-friendly ones. This is the multiverse idea in several flavors. 1. Inflationary multiverse. In many models of cosmic inflation, the accelerated expansion never completely ends. Instead, it stops only in localized bubbles that become individual universes, like ours. Different bubbles can have different vacuum energies and different low-energy physics. String theory's huge landscape of possible vacua gives a natural home for this idea. 2. Cyclic or bounce universes. Some models propose that universes undergo repeated cycles of expansion and contraction, with physical parameters resetting or drifting slightly each time. After enough cycles, you might expect to sample a wide range of values for the cosmological constant. 3. Quantum many-worlds. In the Everett or many-worlds interpretation of quantum mechanics, the universal wave function branches whenever a quantum event with multiple outcomes occurs. Each branch is effectively a separate world with its own history. Typically, this multiverse shares the same fundamental constants across branches, but in more speculative versions, even those may vary. In all of these, anthropic reasoning becomes possible. Observers will naturally find themselves only in branches or bubbles where conditions permit their existence. The improbable value of our cosmological constant stops being surprising because somewhere in the multiverse, every allowed value is realized. Appealing as multiverses and anthropic arguments may be, they raise an uncomfortable question. Are we still doing physics, or have we crossed into metaphysics? Right now, we have no direct observational evidence for other universes. We can't see beyond our cosmic horizon. We can't watch one bubble universe collide with another. We can't hop branches of the quantum wave function. The multiverse earns its keep indirectly by making the smallness of the cosmological constant seem less like an incredible coincidence and more like a selection effect. But selection effects are hard to test. Two people can look at the same data and disagree on whether the multiverse hypothesis is justified. Similarly, we have no direct evidence for gravastars, white holes, or traversable wormholes. What we do have is a network of tested theories, general relativity, quantum field theory, that allow these structures in certain regimes in a long history of predictions that were once purely theoretical but later turned real. Neptune was discovered because the orbits of Uranus didn't quite match Newton's predictions. Mathematicians calculated where a hidden planet would have to be, and astronomers pointed their telescopes there and found it. Paul Dirac's equation for the electron implied the existence of a positively charged twin, the positron, years before anyone saw its track in a cloud chamber. A hot Big Bang model of the universe required a leftover glow of microwave radiation. That glow was accidentally found in 1965 by Penzias and Wilson. Black holes, once dismissed as mathematical oddities, are now routinely detected by LIGO's gravitational wave signals and even photographed in silhouette. History teaches us two things. Many theoretical predictions do eventually turn up in nature, but many others don't. The job of physics is to sift the possibilities, sharpen them into testable predictions, and see which ones survive contact with data. So where does that leave our cast of exotic ideas? Gravastars and other exotic compact objects are viable solutions of Einstein's equations under non-standard matter assumptions. Current observations strongly support the existence of event horizons, but can't yet absolutely rule out all horizonless impersonators. Future gravitational wave and imaging data will tighten those constraints. White holes appear naturally in maximal extensions of black hole solutions and in some quantum gravity models. Real macroscopic white holes connected to our universe would likely be violently unstable. Tiny quantum-induced white hole remnants remain a speculative possibility. Wormholes in parallel universes emerge from idealized spinning or charged black hole geometries, but almost certainly don't survive realistic perturbations. Traversable wormholes would require forms of matter that violate known energy conditions. Dark energy and the cosmological constant problem are undeniably real. The acceleration of the universe is measured. The discrepancy between theory and observation is vast and unresolved. Anthropics and multiverses offer one class of explanation, but not everyone finds them satisfying. In all of this, one principle holds. The universe doesn't owe us simplicity or comfort. It only owes us consistency. Our task is to follow that consistency wherever it leads and to keep testing it against what we see. Some of the most fascinating objects in physics today, gravastars, white holes, multiverses, may turn out never to exist anywhere in reality, or they may be waiting just beyond the limits of our current instruments to be revealed like black holes were in the last century. Either way, the act of working out what could exist, given the rules we've tested so far, is itself one of the triumphs of science. Mathematics lets us Sherlock Holmes the universe, deducing entire classes of phenomena from a few basic clues. If we've read the clues correctly, somewhere out there may be stars built from vacuum, regions of space-time you can exit but never enter, or other universes with very different cosmic rolls of the dice. And if we've read them wrong, then the next generation of observations will show us where we misstepped and point us to new, maybe even stranger, ideas. Either way, the universe is not short on surprises. We just have to keep looking up and keep asking what might be hiding in the equations, waiting to be found.